Hi everyone, my name is Victoria Rodriguez. I'm here to present my work on predicting cognitive states using machine learning fusion paradigms to reduce model uncertainty. So I will go through our motivations, some prior work, the challenges and the insights we have for this problem, the methods we're using, our research question, the results, and a brief conclusion. Our motivation here is safety. A safety analysis showed that distraction is the #1 cause of accidents in aviation. And this distraction may occur either because the flight crew would make a decision based on an incorrect reasoning, or because the flight crew would be focused on one instrument or one response and would leave out the rest. And we have these 4 states, which we call attention-related human performance limited states, or AHPLS. These are the 4 states we're looking for here is channelized attention, startle surprise, low workload, and high workload. The objective of this system is to capture, characterize, predict, and mitigate. In this work here, we're looking especially at the characterize and the predict phase. The limitations we have are there's a limited number of experiments that apply proper cross-validation methods, which may lead to over-optimistic validation results. There's little prior work on the field focused on AHPLS prediction. There's not much data on the aeronautics scenario. Most of the research to date use a single physiological modality, which leaves a gap for multimodal physiological sensing, the possibility to explore sensor fusion. The EEG feature extraction methods we have fail to capture the time-frequency dynamics of the EEG, and multi-class classification is rarely investigated. And when it is, it's usually on different levels of the same cognitive states, not different cognitive states. So the research questions we have for this work are: how subject-independent versus subject-dependent cross-validation affects accuracy? How accurate can we predict in a 2-class versus 3-class versus 4-class scenario? Which subsets of features are the most relevant for multi-class classification? Is the proposed engagement index measurement a better predictor than the usual engagement index calculation? How does the fusion of multi-class model perform versus the classical methods presented? Our challenges here are: how do we ensure that each model is being tested and evaluated on a fair data set? The challenge of not having much research on classification accuracy for AHPLS, especially multi-class and multimodal scenarios. The problem we have when we increase the number of classes and when we add multiple modalities to the problem, which leads to uncertainty to the decision boundaries. When we use multiple physiological modalities, there's a probability that each subject of the features may be useful to characterize different classes. And how do we capture the time-frequency dynamics of EEG? So to overcome these challenges, we propose subject-independent cross-validation that should provide realistic results. We will join 2 AHPLS datasets in hopes that it will help us generalize our models and lead to better accuracy in prediction. We'll compare the prediction power of groups of features. We'll use EEG wavelet decomposition to better capture the time-frequency dynamics, and we will propose a new engagement index calculation, and we will present a sensor fusion framework. For cross-validation, we're doing a subject-independent cross-validation where we have n iterations for n pilots. In each iteration, we're leaving one pilot out, training on all the other ones, and then testing on that pilot. For our binary versus multi-class classification, we'll join our 2 AHPLS datasets. We have 2 datasets called Scenarios for Human Attention Restoration Using Psychophysiology, which we call SHARP1 and SHARP2. These datasets, they're very similar. They're all made to induce those 4 AHPLS states. And we have EEG, ECG, and respiration data. And in this case, we're using only the benchmark data. When we combine these 2 datasets, we have 38 subjects total. To evaluate the importance of feature subsets, we're training each combinations of classes into 3 different subsets, which is EEG and ECG, EEG respiration, respiration and ECG. These are the types of features we have. So we have heart rate variability. We have 2 types of engagement index: activation variancy, intensity, rank order entropy, and respiration. In total, we have 126 features. For the classical engagement index, our calculation is usually done by the sum of beta over the sum of alpha plus the sum of theta over time. What we're proposing here is an engagement index that has a value for each time instance, and from this we can derive three measurements, which is the sum over time, the mean, and the standard deviation. For this, we're not using Fourier transform, which is commonly used. We're using wavelet decomposition, so we have the intensity across time of each frequency. Here's a video to show you how it works. So here we have our EEG over time, and we have the Fourier transform analysis for each window. We're looking at windows of times of 5 seconds. And here we have the time frequency intensity analysis. So this window here would be the theta frequencies, this would be the beta frequencies, and that would be the alpha. But here we have alpha, beta, and theta across time. So you can see that with the current engagement index, this is the only information we're reporting. That's the sum of a 5-second window, and we're losing all that information. So with our proposed engagement index, we have a dynamic engagement, and we have the mean, the standard deviation, and the sum of each. We can see how the dynamics across time can be seen here, how it compares to what we're seeing in the intensity analysis, and with that we can have a lot more information. Finally, we have our sensor fusion approach. We're proposing a framework that we call naive adaptive probabilistic sensor fusion, or NAPS fusion, and it's a framework that utilizes many small random feature sets with bagged models with augmented responsive variables. So with this approach, we're aiming to reduce the model uncertainty caused by the data structure. We're trying to better handle subject-to-subject variability, detecting anomalies, and maintain modularity for future modalities and features we may add in the future. Here's our results. We have, when it comes to the cross-validation effects and accuracy, we can see that if we do a subject-dependent cross-validation, we have an average accuracy that's 98% in a 2-class problem, and 97% in a 3-class problem, and 96% in a 4-class problem. This will lead to over-optimistic results. Now, when we do a subject-independent cross-validation, we see much more realistic results, which is 65% accuracy for 2-class problems, 39% accuracy average for 4-class problem. This is clearly a drop in accuracy, but we know that with this approach we'll get realistic results to use in a real-world problem. Overall, our accuracy for a 2-class problem was 65% with an F1 score of 0.69. For a 3-class problem, we have an accuracy of 47%, an AUC of 0.63, and an F1 score of 0.51. And for a 4-class problem, we get an average of 39% accuracy, 0.61 AUC, and 0.41 F1 score. When we're looking at the subsets of features that are most relevant for multi-class classification, for our research question on most relevant subsets of features for prediction, like we expected, each modality may be useful to characterize one stage. So here, for example, we can see that EEG and respiration has a better accuracy when predicting on channelized attention in high workload, with 66% accuracy than respiration and ECG. But when we look at startle surprise in high workload, for example, respiration and ECG has a 72% versus a 63% than EEG and respiration. And this happened, for example, again, when predicting channelized attention low workload, EEG and respiration is better than respiration and ECG, but for startle surprise in low workload, respiration and ECG is a better option. This difference is more clearly on the binary classifications. When we go to multi-class classification, overall we can see that the best results we get with EEG and respiration. For our proposed engagement index, when we compare to the classical engagement index calculation, we can see great improvement, especially when we're looking at high workload instances. So when we have high workload, we can have, for example, here we have low workload and high workload, and we have an accuracy improvement of 16%. We have a 21% improvement when predicting on star surprise, low workload and high workload. And overall, for a 4-class problem, we have a 7% accuracy improve, a 5% F1 score. For a sensor fusion problem, this is still an ongoing research, and we expect that our approach of a one versus all voting committee will lead to a more generalized binary models. What we do here is since we have such good results on 2-class problems, these frameworks can take those binary problems we showed, which have the best accuracy overall, and we can use those binary models in a one versus all approach. So with this, we believe we'll see better prediction accuracy overall, especially for multi-class problems. And to end my presentation, this is what we have so far. We demonstrated that incorrect cross-validation can lead to over-optimistic validation results. We showed good accuracy when predicting to AHPLLS benchmark tests. We looked at how each subset of features affect accuracy, and we believe that respiration is essential for prediction. But we also believe that each class has one special subset of features that better characterizes it, and we believe that the NAPS Fusion framework will take care of that. We propose a different engagement index calculation, which showed to be a better predictor, especially for characterizing high workload. Finally, our current research focuses on a sensor fusion approach, and we believe that this NAPS Fusion framework will improve the results we have so far. That's it. Thank you for your time, and if you have any questions, I'm here to answer you.